1.5 to 1.6, Graphing Quadratics by Transformations. When we're looking at graphing quadratics by transformations, we need to do the following. You need to be able to memorize the basic quadratic table. The basic quadratic table is kind of like you would understand it as the parent function. Everything is derived, all quadratics are derived from the basic table. So when you look at the basic table of values, it's based on the equation y equals x squared. Now you see these 5 points here, okay? What these 5 points represent is basically you take y equals x squared and you use these x values, negative 2, negative 1, 0, 1, and 2. So all of these points are plugged in to the x value and then we square it to find the y value. And that will give us our basic table. So all parabolas, all quadratics, are derived from this basic equation. And what you need to do is memorize this table, because we're going to use this table to be able to graph our quadratics. Now we're going to be graphing quadratics using transformations, because this is going to help us graph in the future chapters. All right, moving forwards. In order to graph any quadratic, the equation must be in vertex form, and this is very important. What is vertex form? Well, it looks like this, where A, H, and K are numbers. So we're going to go through and identify what A, H, and K do to a parabola in order to see how it gets transformed. So the first one, A. A is a number, and if that number is bigger than 0, it means that, again, if it's positive, the graph opens up. So if this number right here is a positive number, it opens up. Another thing to note is if it's negative, the graph opens down. So you're going to have a parabola that opens up and a parabola that opens down, depending on just the sign of that A value. Now, if the number itself, now be careful, this is very important, the number of A, so the number, not the sign, that's what this absolute sign means. So these bars on either side of A means the absolute of A. That means we're looking at the number and not the sign. The number, not the sign, greater than 1, means that the graph stretches vertically by a factor of A. It stretches vertically by a factor of A. If the absolute of A is between 0 and 1, okay, so again, absolute of A, so the number that's here is between 0 and 1, so it's smaller than 1, it's like a half or a third or a quarter. The idea if this number is a half, a third, or a quarter, so that's this number right here, not the sign, don't forget, then we can say that what happens to the graph is it gets compressed vertically by a factor of A. So it gets squished vertically, and it ends up looking like it's actually wider than it should be. So we're going to be looking at examples of this. Now, we've dealt with all of the things that A can do. So A can open, it determines the opening, and A also determines whether it gets stretched or compressed. Now, it'll never do both, but it definitely will do either stretch or compress vertically. Next, so now we've worked on A, we're going to focus on the letter H. What does H do to the parabola? Well, funny enough, H actually moves things horizontally. But what's more important is you actually have to look inside the bracket. As soon as you add brackets to equations, it kind of makes it look a little funny. So what we want to do is understand that when it's placed inside brackets, it's the opposite of what we see. We see a minus h in brackets, but what we have to think is plus h. So x minus h means instead of minus h inside the brackets, we're going to, opposite of what you see, what is the opposite of minus h? Yep, that's right, it's plus h. So we're going to translate the particular function, write h units. That's right, Even though it looks like minus h and you think you're going to go left, you're actually going to go right. So opposite of what you see inside the brackets, we're going to move right h units. And that's very important. It's opposite of what we see inside the brackets. So every time you see a minus in the brackets, we're actually moving to the right. Now, next part. You see x plus h all squared. So again, inside the bracket, you'll see a plus h. What that actually means is the graph translates left h units. Now, very important here, the word translate. What does translate mean? It actually means to move. So it actually moves the graph. If there's x minus h inside the brackets, x minus 2, x minus 4, we're saying that it moves to the right, translates to the right h units, whatever that number is. Now, if it's x plus h inside the brackets, well, then we say it translates left h units. Okay, moving on. Oh, before I forget, let's talk about this. X equals h. So if x equals whatever number this is an equation that represents the axis of symmetry. Now, the axis of symmetry is derived from what's inside the bracket. We set that equal to 0. And then we solve and we see that it's x equals h. X equals h is known as our axis of symmetry. What that is a line that divides the parabola in half and it cuts it into exactly 2 equal pieces. So last part, y equals a, x minus h squared plus k. So now we're going to focus on the k. What does the k do? Well, the k plus k means that the graph translates up k units. Minus k means the graph translates down k units. So again, our k is on the outside. So it's after the square on the outside. And what it does is it moves up, folks, or down, depending whether it's plus or minus after it. And we're going to see examples of that to better understand what a, h, and k are. Another thing that helps us is that h and k combined together form the coordinates that represent the vertex. So hk represents the vertex of the parabola. And this vertex is very important because that's also where the axis of symmetry lies, going right through that vertex, cutting the parabola in half. So we'll see some examples coming up. So here's an example, and I'm going to ask you to describe the transformations of this function. What's actually happening? So what we're going to do is we're going to look at every piece. If you see here, these are all the things that affected our x squared. Remember, x squared is the basic parabola, and everything from that is derived. It has changed that basic parabola to be something else. So we're going to focus on all of those pieces and describe the transformations. So, number 1. So I repeat, all parabolas come from the y equals x squared, so from the parent graph, and now we've transformed it to be this graph. So what happened? Well, we've labeled each piece so that you can understand that the first thing that we see is that negative. Remember, if a is negative, the graph must open down. That's right. And then we look at the 3. What does the 3 do? Well, I hope that you're looking at it and saying, oh yeah, that means that the graph stretches vertically by a factor of 3. Now, very important, make sure you have all of these words, because if you're missing some of the words, it actually means something else mathematically. So I need you to actually write out these words as you see here. The next piece, remember that it's now inside the brackets, and because of these brackets, it's thrown everything off. So inside these brackets, we're looking at a minus 4. Is it really minus 4? No, that's right. When it comes out of the brackets, it becomes plus 4. So which way are we moving? We're moving, translating to the right 4 units. And then we look out here, and what is this saying? Well, this is saying translates down 1 unit. So each of the pieces plays an important role in the transformation of a quadratic. Now the vertex is 4, negative 1. The axis of symmetry is x equals 4. This is the full description of the transformations. So another way that we do this is I get you to learn about, to describe the transformations using an acronym. The acronym we're going to use is VOAT. VOAT basically will state all the different pieces you need to be able to successfully answer the question of describing the transformations. Specifically, we're looking at each of the pieces that changes the changes that were made to create this graph from the original y equals x squared. So, starting with the beginning, let's do all the different pieces. V stands for vertex. What is the vertex of this particular parabola? Well, that's negative 2, 3. Next, opens down. O stands for opening. Which way do we open? Well, it opens down because of the negative. A is the axis of symmetry. What is the axis of symmetry? It will be x equals whatever it is on the number on the inside. X equals the x on the vertex. However you want to understand it, it's basically you take the number on the inside of the brackets and you pull it out of the brackets and it becomes negative 2. So x equals negative 2. Another way to do axis of symmetry, it is always the x value of the vertex. Okay, moving on. T is all the rest of the transformations. So we've already dealt with opening down. We've already dealt with, oh, no, we've not dealt with this. What is this? What does this half do? Well, I hope you're thinking, okay, it must compress vertically by a factor of a half. And you'd be right if you said that. So it compresses vertically by a factor of a half. What does this plus 2 do? Well, we know that it translates left 2 units. And what does this plus 3 do? Well, that one translates up 3 units. So this, folks, is the end of describing the transformations. Moving on. Example 2. You're asked to create a table of values. When you create the table of values for a quadratic, essentially what we're doing is creating the situation where we can actually graph the parabola. So, when you create a table of values for an equation like this, you must start off with the basic table. What is the basic table? X, Y, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. And then we need to now transform these coordinates to our new coordinates based on this equation. Well, everything on the outside applies to the y. Everything on the inside applies to the x. But remember, the inside is affected by brackets. So it's not really x minus 4, but actually x plus 4. That's right, because don't forget, this is the same example we had earlier. This moved to the right 4. To the right 4 means you move plus 4 along the x. And then we know that there is opening down, so that affects the y, times 3 because you're vertically stretching it. So you're going to take negative 3 times the y value to stretch and flip it upside down. And then we're going to do minus 1. Minus 1 means we're translating 1 down. So negative 3y minus 1. And now what we're going to do is plug in all of these x values into this x part of the equation. Then we're going to plug in all these y values into the y part of the equation. Go ahead and do that. And when we do that, we get these values, 2, negative 13, 3, negative 4. Now you might be wondering, I'll explain this part in a second, but I first want you to understand where I got 2. Negative 2 plus 4 is 2. And then this 4 gets multiplied to negative 3, so 4 times negative 3, and then minus 1, which is negative 13. And again, do the next one. Negative 1 plus 4 is 3, and negative 3 times 1 minus 1 is negative 4. So this is the next one. Hopefully you're starting to see a pattern. The x's will always follow a pattern because they originally followed a pattern. So the next number is going to be 4. 4 what? Well, 4, and we plug it into the y, the 0, and we find out we get negative 1. Hey, I know this coordinate. Where have we seen this coordinate before? That's right. You should be able to see that this is the vertex. 0, 0 is the original vertex. It moved to 4, negative 1. So the coordinates hk turn out to be the middle point in the table of values. Neat. And we can always check to make sure that we've done it correctly by checking the vertex from the equation. Next, so we see our x pattern going 2, 3, 4. Hopefully you're thinking 5, 6, because that's what I'd be thinking, because I'm always looking for a pattern. Now, next part. Notice the y values also have a pattern, not in the sense of how they go down and up, but the fact that they repeat each other. So 4, 1, 0, 1, 4. So these numbers are actually repeating each other, with the exception, obviously, of the vertex. So what numbers are going to go here? That's right, -4. What number will go in the last one? You got it, -13. So now, folks, what we have is a table of values representing this equation right here. All right, let's try another one. Originally, we had this one, if you remember. And what happened when we had this is that we have to also be able to create the table of values. So here we go. X minus 2, remember, opposite of what we see inside the brackets, x plus 2, we want x minus 2. And then the outside values are 1/2 y minus 4. Now, this is a lot of information, so we're going to move a few steps back. We know this information here, and we know the basic table. That should be standard. So how do we get the numbers? That's right. What you're going to do is plug these numbers, the x values, in for x, the y values in for y, and we should be able to get the coordinates. So we plug in x equals -2 minus 2, well, that gives us -4. 1/2 times 4 is 2, minus 4 is -2. -1 minus 2 is -3, and 1/2 of 1 minus 4 is -7/2. Now notice I use a fraction. Please give me your answers in fractions, folks. Decimals are not allowed unless I say otherwise. So we continue. We get -3, -7/2, -2, 1, 0. So that's the pattern of the x's. We have our vertex, and now we can find the y's. And folks, that is the table of values for this equation. Again, you're following what the numbers did to the equation. Next, example. If you're given this and you're asked to graph it. So we already did these, if you remember correctly. So these values I'm just going to repeat here. We've already done these table of values, but we're going to graph our function. So what are we going to graph? Well, I only have positive x's, so I do not want to see any negative x's on the graph. So that's why I'm putting the y-axis, so only the positive x-axis is shown and not the negative. The next thing to note is that the y values are all negative. That means I'm pulling my x-axis right to the top so that I don't see any positive. I only deal with the negatives. The next thing you need is a scale. So we're going by 2 blocks along the horizontal and by 1 block along the vertical. And now we're going to plot our points. 2, -13, 3, -4, 4, -1, 5, -4, and 6, -13. And look, folks, there's our parabola. Not just yet. We have to draw a smooth, rounded curve, okay, and no pointing. That is, I want to see an actual parabola and not a random version of a parabola. I need to see smooth, rounded curve only. Otherwise, there will be a penalty. All right, that's the end of this part of the lesson. We're going to continue with the next part in just a second for 1.7. All right, so moving forwards, I want to retouch on some of the concepts. So we're going to look at some more quadratics, and we're going to describe the transformations, and we're going to state the domain and range. That's something that we didn't cover in the last part. So let's look at some more graphs and continue on. So you're asked to graph. When you're asked to graph, you'll probably be asked to describe, and when you're asked to graph, you need to do a table of values. The domain and range is the extra stuff that you might be asked. To describe the function, we need to state the vertex, which is 3, negative 3. How do we know what that is? Well, it's this 3, folks. Remember that this negative 3 inside here changes to a positive, and this minus 3 over here stays as a negative because it is on the outside. Remember, only the inside changes, and that's why we have 3, negative 3. O stands for opens. How does this graph open? Well, let's see. Right after the equal sign, the sign is positive, so this graph opens up. A stands for axis of symmetry. Axis of symmetry is the x value of the vertex, our h. What is our h? The h is 3. So the axis of symmetry is x equals 3. And the transformations, well, to describe the transformations, we stretch vertically by a factor of 3, translate right 3, and down 3. And folks, that's the end of the transformation part of this. Okay, we need to state the domain and range. So, domain of a parabola is always x belongs to real, always. The range is y belongs to real, and we have to look at the vertex in the opening. The vertex says it's 3, negative 3. Because it opens up, what we're looking at, if you want to give yourself an idea, you're looking at a parabola that goes like this. And what it is the vertex point down here is 3, negative 3. How low does it go? Well, it starts at negative 3, and it goes up to infinity. So y is greater than or equal to negative 3. And that, folks, are the state and we've done the domain, the range, and we've now stated the transformations. Next part is to graph. What do we do when we graph? Well, when we graph an equation, what we need to be able to do is state the table of values. XY is our beginning coordinate. Remember that the very first set of coordinates is going to be your basic table. That's the table I made you memorize. So XY. And then the other part is going to be its transformations. Remember, instead of x minus 3, it's x plus 3, and the y value is 3y minus 3. So we have all of that. Let's plug in the coordinates. And we plug in our coordinates, and guess what, folks? We get 1, 9, 2, 0, 3, negative 3, 4, 5. Okay, so notice it's going in a pattern 1, 2, 3, 4, 5. And what do the y values do? That's right, they repeat. You get 0, and then you get 9. So now we need to graph this. What do you see? All the x values are positive, so I don't want to see any negative x. And most of the y values are positive, so we're going to draw that x-axis a lot lower. So we have f at x, we have x, don't forget that I want to see a good use of space. So there is no wasted space here, because when I graph the points, as we see here, graphing these points, I can get a smooth, rounded curve with no pointy edges, folks. None at all. Moving forwards. Example 2. Given the graph of a parabola, determine the equation, domain, and range. So now what I'm going to do is give you guys the graph. So here's the graph. And I need you to find the equation of the parabola. This is a little more difficult, and I would even classify this as more inquiry. So problem solving, because you're actually trying to solve the problem here of finding this equation. So there's multiple points we can deal with. Look at all these points. There's 5 of them, folks. But only one of them is the most important point to find the equation. That's right. The most important point is going to be that vertex. But before we do that, let's just get rid of the domain and range. What is the domain of this function? You're right. X belongs to real. Range of this function? Well, range is g at x belongs to real, because remember it's not called y, it's actually g at x, belongs to real, such that, yes, that's right, all the values from here up. So that means it's g at x is greater than or equal to negative 7. Now that we've got domain and range out of the way, let's try to find our equation. So there are different ways to approach this question. Essentially, what we're trying to do is find that a value. That's the part we're missing. We're missing an a value. We know our h, we know our k from the vertex, 1, negative 7. So we're going to do some algebraic solving to find this answer. But before we find that answer, I want you to understand by looking at the graph, you can actually tell if it got stretched or compressed, which will help us in our final answer in a little bit. So I'm going to insert the basic. See this basic graph? All I did is he was originally here. Remember that basic table? It's usually -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Well, all I did was I took those coordinates and I moved it down to match over the vertex. So this is our actual basic table moved. And what happened is that what happened to the blue graph from the black graph? The black started. How did it move to a blue graph? Well, folks, what do you think happened? Oh, I know what you're thinking, and you're right. The graph, this blue graph, was compressed vertically. And because it was compressed vertically, it's going to tell us that this number should be between 0 and 1. It's opening up, so we know this number is going to be positive. Positive and between 0 and 1, that at least narrows our field down. All right, so we need to find the equation. How we're going to do that, I'm going to show on the next screen, so we know it's compressed. So we're going to take the coordinates 1, -7, and we're going to sub it for h and k in the original equation. And then we're going to take another point, any point you want, folks, from that previous graph. So any point over here from the previous graph you can use. And again, it's only these points over here on the blue graph is the ones we want. We need to use these blue points to find our answer. All right? Now, to do that, we plug in one of the points, which is 3, -5, and we're substituting it for x and y into the equation. Y equals ax minus h squared plus k. Now, plugging it in, what is y? Let's look here. What's y? We sub for y, -5. That's where it came the -5. A is a. We have not found it yet. Next, we know x. X is here. X is 3. So we plug in 3. We know h is 1. We plug in, so this will be x minus 1. X minus h. 3 minus 1 plus k. Well, let's see. What's our k value? K value is -5. So we're going to subtract, our k value, that was a mistake. K value is not 5. Our k value is over here, folks. Our k value is -7. So we have our equation right here. We need to solve for a. So the next step is -5 equals, we deal with the bracket on the inside. 3 minus 1 is 2. Squared makes 4. 4 and then -7. Now, very important, this 4 is attached to a. They cannot go together, these two, because 4 is still attached to a. So we've got -5 is plus 7 is equal to a times 4, or 4a. So again, -5 plus 7. So we move the -7 over. It becomes -5 plus 7, and then equals 4a. So we divide by 4, and you get the answer. A equals 1/2. And so the equation of this parabola is going to be a equals 1/2, so g at x equals 1/2. X minus 1, where did we get that? That's right, we got it from the vertex. And then -7, which we also got from the vertex. And that's our final answer for this question. Moving forwards. Now there are different ways that we learn how to do this. Okay, another way that you can find the equation of the parabola is to look at the original table of values and how they got transformed. This is a little harder concept to understand, and it's not necessary for you to know how to do this. Moving forwards. Example number 3. A football is thrown into the air. Its height h at t of the ball in meters after t seconds is modeled by this equation. And you're basically asked how high off the ground was the ball when it was thrown. So to do that, you have to imagine, when does time start in this question? If you're about to throw the ball, Is it when you're about to throw the ball or the moment the ball leaves your hand? Oh, that's right. It's the moment that the ball leaves your hand. So, if we look at an example, here's an example. Here's our coordinates, 1, 8. I know the graph opens down, and it does something along those lines. Not exactly, but it's pretty good. Now, what is this asking? Don't forget, it's asking how high was off the ground was the ball when it was thrown. That means the ball has not even left your hands. It's the instant, the moment that time starts. Okay? And that means that's when time is 0. When time is 0, we can find some important pieces of information. For example, when we plug in the equation, and I want 0 to find out when the time is 0, I plug in 0 for t. When I plug in 0 for t, we get an answer of 3.1 meters. Now, when you answer a question that involves this, what you need to do is hand it in to someone else and have them verify that you've done it correctly. Okay, moving forwards. The ball was 3.1 meters above the ground. Next one. What was the maximum height of the football? Well, you had an equation. In that equation, the vertex is clearly evident. The vertex helps us find the maximum height. So we take the vertex, and the maximum height it reaches is this value here, the y value, the g at x value. And we say that it opens down because a is less than 0, and so it opens down because a value is negative. How do I know it's negative? We talked about it earlier, and I can show you, as well as it opens down because a is negative, and the maximum height is at 8 meters, okay? We'll talk about why it was opening down in just a second, okay? This is a graph that's going, you throw it in the air, and whatever comes up must eventually come down. That's why the graph looks like this. Automatically, you should be thinking, okay, my coordinates had better be negative. Yes, so the y value must be negative. And the maximum height of the ball is at 8 meters. Next, part C. How high was the ball at 2 seconds? Well, we need to know that value. Well, that means we set t equals 2, and we plug it in the equation. H at 2 is equal to, and we plug in 2 for t, we get a value of negative 4.9 times 1 squared plus 8, which means that the value is 3.1. 3.1 meters, that's right. The ball was 3.1 meters above the ground. Okay, moving forwards. We have a part D. Is the football still in the air after 3 seconds? Do we know this? Well, at this point we don't, but what we can do is plug in t equals 3 into the equation to find our h or y value. And when we do that, we find out that h at 3 is equal to negative 4.9 times 3 minus 1 squared plus 8. Negative 4.9 times 4 plus 8 and equals negative 11.6. The football is not in the air because the height is not positive. Look at that. We got a negative height. Is that possible when we're calculating something? And the answer is no. So note, because it's negative, we find out the football's not in the air. Part E, last one, folks. When does the ball hit the ground? This one is a stretch. This one is an expansion of your understanding. How to get that 0? Well, we need to set the height equaling 0. Not t, but the height, the whole thing, equals 0. So we set 0 equals the equation. What do we do next? It's like reverse BEDMAS. Instead of plus 8, it becomes minus 8. 0 minus 8 is negative 8 equals negative 4.9 t minus 1 squared. Next thing for you to do is to divide out negative 4.9. When we divide out negative 4.9, we get t minus 1 squared is equal to negative 8 over negative 4.9. Notice I haven't touched anything, a calculator especially. Why? Well, we're going to solve this without a calculator. Next step, what we have to do is take the square root. We need to take the square root of this function, of this part of the equation, and we get 8 over 4.9. Remember, it's plus or minus. And then the reason why we have the square root of 8 over 4.9 plus or minus is because any number squared, positive or negative, will result in a positive answer. So, for example, I can take -1 and square it, and I get 1. I can take 1 squared, and it'll become 1. So both answers are the same, but the questions were different. That's why we have the plus minus. Next step is, since we took the square root of that, that gives us equals the t minus 1 without the brackets, and then we move the minus 1 over, and it becomes 1 plus or minus the root of 8 over 4.9. And that is the exact answer. You want approximate? Please, folks, I'm asking you to please give me the equations, the answers. If you need to use this way to solve, I need you to use the quadratic formula when you solve, not the quadratic. I want you to make sure that whenever you have these values here, which is exact, I need you to convert it to 4 decimal places. So both parts got 1 plus the number and 1 minus the number. The 1 minus gave us a negative. That's not possible, folks, because time starts at 0. So the ball hits the ground at 2.2778 seconds. So just shy of the 3 seconds we were trying to find earlier. All right, folks, that's the end of the video. That's everything all about 1.5 through 1.7. Have a numerical day.